All right, I kind of like this one. I mean, I like chapters 8 and 9 a lot. I mean, I think a lot of you guys too, because you're starting to get into like maybe how it feels like all of this rigor can be applied to something more realistic and something you could maybe see in your design projects coming up or your career going forward, um, and even just in your everyday life. You just wanted to fix your plumbing system in your house when you get whatever trying you get a little bit um, maybe you get to the point where you realize you can give those things a go, and then you try them out, and then you realize you can't. I don't speak from experience. Um, but so this one is kind of interesting. This says to conserve water and energy, a flow reducer is installed in the shower head. And so we see something that looks like this. So there's our shower head, and let's see, we got flow going in and coming out. This is 1/2 inch. Well, let's just call this D1. And over here we have 50 holes. So D1 is 0.5 inches. And here we have 50 holes that are D2, 0.05 inches. And so then to preserve some water or energy or both, we just put a little constriction there, which is sufficient to reduce the flow. And so the question here is KL for the flow reducer is what? I think. Yep. Let's see. If the pressure at point 1 remains constant, so you can say that by adding this in or not adding it in, the pressure in our piping system isn't going to change. That's pretty well set by whatever the source of that pressure is. So further up the piping system. So P1 is unaffected by flow reducer. I learned my lesson. I'm going to make sure I read this all the way out. All other losses neglected. Gravity neglected. And what we want here is that the flow reducer, it reduces flow by a factor of 2. So this is point 1, this is point 2. Always nice to set up your 2 points and actually label it on your diagram. And so what we have relating here is we have some, it's asking us to relate some information about the flow without the flow reducer, and to relate that to information about the flow with the reducer. And this should be a sufficient amount of information. In fact, the only thing you need to know here is that P1 is unaffected, our flow rate reduces by a factor of 2, and that the diameter, that we have 50 of these that are, this one is 10 times smaller than this one. And with that, there's enough to actually determine the loss coefficient here. So let's say without reducer, energy equation from 1 to 2 gives us P1 over gamma plus V1 squared over 2G plus Z1, which we already said our elevation changes are going to be neglected here. Plus the head loss, and now it says all other losses are neglected. So before we put in the reducer, that just is nothing. Gravity effects are negligible, or the elevation changes are neglected. Pressure at 2 is just 0 because we've hit atmospheric. It's a free jet. 50 different free jets there. And that's about it. Here we actually get to see our continuity get used. So continuity to relate V1 and V2. So there's our areas, the 50 times those tiny little holes. And all of this is our flow rate, Q, right? So equals Q. And that's our initial flow rate. So now, let's see here. Let's just leave it like that for now. We might come back. Let's just get all the information on the page with reducer. So now what do we know? Well, the flow rate is going to be reduced by a factor of 2, which means our velocities will be reduced by, proportionally to that. But let's now apply our energy equation again from 1 to 2. And we have P1 remains unchanged. V1, I'm going to put a little squiggle over the top to represent this is now with our reducer. And we'll just leave that out because we know it's 0. We know that's going to be 0 still. V2 squiggle squared over 2g. Plus now we do have a head loss. And our head loss is now KL V. Well, we'll just call it squiggle squared over 2g. And if I do this correct, so this is actually, we know that the V squiggle for our flow reducer is actually just going to be, the velocity. This is supposed to be a uniform cross section here. So this is just V1. Does that make sense? So this is, in general, the velocity you would get across it, but assuming that we still have the same cross section pipe. And if it was a different cross section, you could relate it. Because we have enough information about our flow rate. So with this, let's say, well, let's just, like I said, we'll get all the information down on the page. Continuity with a squiggle over it now looks like V1, A1, V2, A2, which is going to equal this Q over 2. Okay, so let's see here. We have 1, 2, 3, 4 equations. We have V1, V2, both of them squiggled. That's already 4 in pressure. And the flow rate itself. But actually, there's hidden equations in here. Okay, actually, so we have this equation, which is 1. We have this is equal to Q, which is 2. We have this is equal to Q, which is 3. We have this equation, and then we're going to have the same 3 down here. We actually have 6 equations, and our unknowns are P1, the 4 velocities involved in Q. So we have enough equations and enough unknowns. I know it seems like a ton right now, but we do have enough equations for the unknowns. So let's do, let's be smart about this and take our A, and this will be our A equation with the tilde, and take A minus A tilde. This is going to give us V1 squared over 2g minus V1 squared over 2g equals V2 squared over 2g minus, and then minus KL V1 squared over 2g. And actually now all we have, what we can say here is that we have V1 A1 equals V2 A2, which equals V1 A1 over 2, no, sorry, two of these. Since these both equal Q and these equal Q over 2, this equals 2. Okay, so I mean, in a real setting, you could start plugging in numbers right now and go along the way, but you can actually solve this just algebraic here, just through a bunch of algebra, which is what I'm attempting to do. But you can see now we have, there's no more pressure anymore, there's no Q, we've just related our velocities well nicely. The G cancels out, the 2G. And we know that, well, let's see, if we can just write all of these in terms of one of the velocities will be set. So let's choose, what would be a smart choice here? Let's do it in terms of V1 equals 2 V1 squiggle. V2 is equal to 2 V1 squiggle A1 over A2. And V2 squiggle equals V1 squiggle A1 over A2. And then we can solve this for the KL, which is what we want. KL equals, pull that to that side, is just going to be V2 squared minus V2 squiggle squared minus V1 squared plus V1 squiggle squared all over V1 squared. V2 squared, we just go to our lookup table here, right? This is going to be 4 V1 squared A1 over A2 squared, and I'm going to pull out a V1 squared at the end, minus V2 squiggle squared is just going to be A1 over A2 squared. V1 is just going to give us a factor of 4 and plus 1. All of this times V1 squiggle squared over V1 squiggle squared. Those two cancel. A1 over A2 equals that pi D1 squared over 4 over pi D2 squared over 4, but 50 of them on the bottom. And pi 4 cancels. D1 over D2 squared. D1 is a half, D2 is 0.05 squared over 50. So this is a factor of 10, but actually we get 2 of them. Right? 10 squared, which is 100. So A1 over A2 is just 100 over 50, which is just 2. And that makes KL just equal to 4 times 4 minus 4 plus 4 plus 1. Oh, I must have, one of these is wrong. This one, right? Shoot. Or yeah, if that's a minus. Because I mean, I just carried it down wrong. There's a minus there. 16, okay, this is right. That's 8 plus 1, which is 9. Great. So it's a huge loss coefficient. Whew. Should have done that one first. I don't know. The setup of these problems is more important than the algebra, obviously. Yeah.
I did not keep back on the first continuity, first to second.
Well, that's what I was trying to talk through. Was that that's what I was just trying to step through. Is you've just set up a huge system of equations for fairly large number of unknowns, and it's kind of good to like think about that as you go along. How many unknowns do I have in the problem? How many equations am I getting? Do I have enough? And then it's just noticing that you have P1 sitting out there, and then if you subtract the two, you'll remove P from the whole equation, the set of equations, right? I mean, P1 only shows up there and there, or any of the pressures.